Let's say you have a job at an aerospace company. Let's call it Collins Aerospace. Your job is to test, troubleshoot, and repair digital circuit boards that are installed in aircraft. To do this, you plug the board into a computer which runs the circuit board through a series of tests, some of which program the RAM chips on the board with random patterns and then reads the patterns from the board to make sure they match. While testing one of these boards, you get a failure, saying that the value read from an input-output RAM chip is not the same as the expected value. The program expected a hex value A052, but it read a hex value of A050. So what is wrong with the board? What we would do is compare these two values. It is a 16-bit data code programmed to the RAM chip. We know this because it is in hex and is 4 characters long. So there are 16 data lines on our I/O RAM chip, which could be the source of the problem. How we narrow this down is in the expected and read values, A052 and A050 respectively. The first 12 bits read what they're supposed to, A, 0, and 5. It is in the last 4 bits that we have an issue. Let's convert this to binary and see what happens. A is 10, which in binary is 1010. 0 is 0000. 5 in binary is 0101. Now we get to the problem bits. 2 is 0010 and 0 is 0000. And there it is. The program expected to read a 1 in that second digit, but read a 0 instead. Looking at the schematic, this is IO1 data line. Following this data line, we're going to come to a resistor. Now let's look at our board. So we notice that this is a surface mount resistor, and it looks broken. So this must be the source of the problem. Continuing your work, you come across another I/O RAM error. This time, the expected value is hex FE71, and the value that was read was hex FF71. Let's write out all the bits this time. There we go. We can see that here we have a discrepancy in the bit. A 0 was expected, but a 1 was read from the data line. This data line is IO12. What do you think we will find when we go down the data line to the resistor? Well, we find the resistor on the board, and it looks fine. So let's put a multimeter to it. The multimeter reads 0.2 ohms. This resistor is shorted, so that is the problem with this board. Okay, so the first test, we expected a 1 to be read, and instead found that it was a 0. This led us to an open resistor on the data line. In the second test, we expected a 0, and we read a 1, which led us to a shorted resistor on the data line. This is nearly always the case when troubleshooting a digital circuit. If you expect to read a voltage, a 1, and instead there is no voltage there, it is likely you have an open in the circuit. The inverse is also true. When you expect there to not be a voltage, a 0, and instead there is a voltage, 1, then it is likely you have a short. When testing a digital circuit, it is important to program a sequence, test it, and then program the inverse of that sequence and test it. This will allow you to find any opens or shorts in your circuit. The first example programmed A052. After this sequence is tested, the testing software would program the inverse of this data. Pause the video and see if you can come up with the inverse yourself. Okay, we already broke this down into binary in the first example. To find the inverse, we flip all the bits. Now, we convert this back into hex. 0101 is 5. 1111 is F. 1010 is A. And 1101 is D. So the inverse is 5FAD. The issue was an open in IO1. which is this bit right here. Notice that in the inverse, the bit is already low. So when this circuit is tested, it won't show a fault. This is why the circuit must be tested with a specific sequence and the inverse of that sequence. I hope this was enlightening for you. In case you were curious, the answer is yes. This is what I do for a living. If you want to see more of these little gems of useful information, make sure you are subscribed and hit that like button. Hit the notification bell to get notified when new videos are posted, plus it helps the YouTube algorithm better promote my videos. Until next time.